Yeah, welcome. So in the last lecture, we have discussed that the performance improvement in the processor, it takes place because of two reasons. Till 1980s, the performance improvement came from architectural and organizational information. I mean, before 1980s, the performance improvement has came from improvement in the transistor technology, right? But after 1980s, the performance improvement was mostly due to architectural and organizational innovations. Architectural and organizational innovation in the sense improvement in the pipeline technology, having more having more uh, number of functional units, all those things. These things comes under architectural and organizational innovation, right? So let us now briefly discuss like what's the difference between a computer architecture and a organization. When we say architecture, basically we are referring up to instruction set architecture, which talks about the instruction set, the registers, addressing nodes, etc. But when you talk about organization is basically dealing with the high level design, like in a processor, how many ALUs will be there, how many logical units will be there, what type of pipelining or control design we are using, etc. Right? So the processor itself, we can view the processor from different perspective. So from the architectural perspective, that is from the instructional set architectural perspective, when we see the processor, so it deals with the what type of functions that a user or a programmer does with the processor. So basically, it talks about opcodes, addressing modes, registers, etc. So these things are the architectural perspective of the or architectural view of the processor. And processor can also be viewed from an implementation level. This implementation view is otherwise called as microarchitecture, or it can also be called as designer view. So this includes the logical structure or organization that underlies the architecture. This represents the logical structure that underlies the architecture, which includes pipelining, functional units, caches, registers, etc. Okay. So this mostly talks about pipelining and other functional units. And then we can also view the processor from a realization viewpoint, which represents the chip design or system design view. This represents the physical structure that embodies the implementation. It talks about gates, transistors, wires, so on and so forth. Okay. So if you consider the instruction set architecture, so where it comes. So basically it comes between the hardware and the software. At the lower level, we have the hardware. On top of that, we have the instruction set. On top of that, the other softwares were defined. So this is something like a level of abstraction. This is one, the hardware is one level of abstraction. Instruction set is another level of abstraction, and software is another level of abstraction. So why should we have this abstraction? What is the advantage of having this abstraction? So with these abstractions, the technology or the architecture will last through many generations, which is called as portability. It is any change can be done without affecting the other. You can change hardware without making much changes in the instruction set or the software. Similarly, you can change the instruction set without updating the hardware or the software, right? And it can be used in many different ways. So we get generality by abstracting. So the interlinkages between the different blocks will be reduced. So when you abstract things, no, there is no interconnections between software and instruction set. But still, the software can use the instruction set. So there are no bondages. So that's the point. And it provides convenient functionality to the higher levels. The lower level provides convenient functionality to the higher level. Hardware provides functionality to instruction set, and instruction set provides functionality to the software. And also it permits an efficient implementation at lower levels. So these are the advantages of having abstraction. And coming to today's topic, we'll be discussing uh, how the how can we evaluate the performance of a processor. So there are different ways to evaluate the performance of the processor. Some of these things we'll be discussing. So first, what we'll be discussing is something called as Andhals Law, which we have discussed in operating system also. So in general, Andhals Law is given something like this. The speed up of a processor can be measured like this. Say assume that you have a processor which is executing at one speed, but later we have made some improvement in the technology so that its speed is increasing. Now, how can we measure its speed up? How much speed it has got increased? How do we know that? So that can be measured by using a generic formula like this: execution time for a task without enhancement. So the processor, before getting enhanced, what is its execution time for a given task, divided by execution time for the task using enhancement. After enhancement, when the same processor is used to execute a task, how much time it takes. So divide that. That will give the speed up. Okay. So there are two things here we are going to discuss in Amdahl's law. One is the new execution time. What is the new execution time? And what is the overall speed up? The new execution time can be calculated like this. The new execution time will be equal to the old execution time into 1 minus fraction enhanced. How much improvement you have done? I mean, the old compared to the old processor and to the new processor, what is the amount of enhancement done? That is called as this fraction enhanced. 1 minus fraction enhanced plus fraction enhanced by speed up enhanced. Okay. Say for example, 10% improvement was done. Then in that case, fraction enhanced will be 0.1. So 1 minus 0.1 will be 0.9, right? And here also fraction enhanced will be 0.1, right? Okay. Speed up enhanced. Say because of this 10% improvement, because of this 10% improvement, the processor speed doubles. Then the speed up enhanced will be 2. Because of this 10% improvement enhancement, if the processor speed triples, then the speed up enhanced will be 3, so on and so forth, right? And then the overall speed up is calculated like this: old execution time divided by new execution time. So here let us assume it is old execution time. At the top we have old execution time divided by new execution time. What is new execution time? This equation. This equation also includes, starts with old execution time. Old execution time into all these things. So old execution time and all these things. So this old execution time and this old execution time will get cancelled. Finally, what you will have is 1 by 1 minus fraction enhanced plus fraction enhanced by speed up enhanced. So that's how we got this equation. Okay. So this is the same thing as what we have discussed here. Now we'll discuss one example. Assume that floating point instructions were improved in a processor such a way that the processor speed becomes 2 times faster, right? And instructions were improved in a processor such a way that the processor speed becomes 2 times faster. But say that there is actually only 10% of instructions are floating point instructions. Generally, if you take a typical program, the amount of floating point instructions will be only 10%. But we have made some improvement in the floating point instructions, which improves the processor, which improves the runtime to 2 times faster. Now, how can we calculate the new execution time and overall speed up? That is given something like this. The new execution time will be equal to old execution time into, what is the formula? 1 minus fraction improved. So 1 minus zero point 0.1, which is 0.9, plus fraction improved, that is 0.1, divided by speed up. Speed up is 2 times, it becomes faster, so it is by 2, right? This what is old execution time, that we don't know, so leave it as it is. So the result is 0.95 into old execution time. And what is speed up? Speed up is equal to old execution time by new execution time. So old execution time we don't know, by new execution time is 0.95 into old execution time. So the numerator old execution time and denominator old execution time will get cancelled, and what you get is 1 by 0.95, which is nothing but 1.053. This is the speed up achieved. Okay. So there are many ways to measure the performance. For example, if if you say that uh, if you say that a particular processor X is n times faster than Y, then it is given something like this: execution time of Y divided by execution time of X is equal to n. In that case, we can say that X is n times faster than Y. Or if you want to measure in terms of throughput, throughput represents the amount of tasks completed in a unique time. Throughput of X is n times faster than Y, n times that of Y. You can say like this: if the tasks per unit time X by tasks per unit time Y is equal to n, right? The throughput of X is n times that of Y if it is satisfies this equation, right? But normally it is not that easy to calculate the performance. Assume that a particular processor, a typical processor, in a typical processor, GUI is 10 times faster than Y on X. Okay, is in the processor X, GUI is 10 times faster than Y, right? But with respect to file operations, with respect to file operation, X is 1.5 times faster than Y. With respect to arithmetic operations, X is 2 times faster than Y, so on and so forth. So basically we cannot generally we cannot say that X is this much time faster than Y. The reality will be something like this. In some applications, the processor X will be so many times faster than Y. In some other application, the processor X will be faster than Y with some other parameter. In such cases, how we will define the uh, how we will be defining the performance, right? Similarly, maybe in memory operation, X may be 3 times faster than Y. So in such cases, what we will be doing? That's the question. So can we go for can we measure the performance of the processor based on CPI clock cycles per instruction, or can we measure the performance of the processor based on clock rate? So the execution time of a processor is given like this: execution time is equal to CPI into clock cycle time. What is CPI? CPI is cycles per instruction. So basically it is average cycles per instruction into clock cycle time. Clock cycle time is what's the time for one clock pulse. One clock pulse duration may be it may be 1 millisecond, 0.5 millisecond, or zero point 0.1 millisecond, whatever it may be, right? Or it may be 1 microsecond or 1 nanosecond. CPI represents the cycles per instruction. Say for example, a typical program has 100 instructions, okay, and say that first instruction for execution it takes 5 clock cycles. Say the second instruction takes 2 clock cycle. Say the third instruction takes 4 clock cycles. say the next instruction takes 1 clock cycle, so on and so forth, right? Then say this typical program contains n number of instructions, then n number of statements or instructions. Then we add all these clock cycles. And divide it by n. As a result, what you get is called a CPI. As a result, what you get is called a CPI, cycles per instructions. At an average, how many cycles is required for one instruction? That is how the CPI is calculated. And execution time is calculated as CPI into clock cycle time. Right? Now, if the CPI is higher, that doesn't mean that you cannot say that that processor is better than some other processor. Or if the clock rate is higher, then also you cannot say that this processor is better than other processor. Clock rate represents the number of cycles per second. CPI represents the cycles per instruction, whereas clock rate represents the number of cycles per second. Okay. So here is one example for calculating overall CPI. Again, CPI also may vary for different instruction. For example, let us assume that in a for ALU operation, CPI is one clock cycle. If it is an arithmetic or logical operation, that can be done in 1 clock cycle. Load instruction, say it can be executed with 2 clock cycles at an average cycles per instruction is. Say store instruction can be executed in 2 clock cycles. Say branch can be executed in 5 clock cycles. And let us assume that typically in a program, 40% instruction will be arithmetic instruction, 27 is the load instruction, 13% is store instruction, and 20% is branch instruction. Then the overall CPI is calculated something like this: 1 into 0.4 plus 2 into 0.27 plus 2 into 0.13 plus 5 into 0.2. So this will give the overall cycles per instruction, which is 2.2. Okay. So this is how we calculate the overall CPI. But CPI is also not an effective measure to measure the performance of a computer or a processor. Similarly, there is another method to measure the performance, which is MIPS and MFLOPS. MIPS stands for millions of instructions per second, and MFLOPS stands for millions of floating point operations per second. MIPS is calculated something like this: clock rate by CPI into 10 to the power 6. Clock rate is cycles per second, and CPI is cycle per instruction. Clock rate by CPI into 10 to the power 6. That is what is MIPS. MIPS also it's not an effective method to measure the performance. So there are 3 main drawbacks with MIPS. The first drawback is MIPS is instruction set dependent. That is, whatever the result or the performance measure given by MIPS, it will not be stable. It varies with a different instruction set. And the second drawback is MIPS varies between programs of the same computer. If you calculate the MIPS of 2 different processors, processor 1 and processor 2, on a particular program, then it will give some 1 MIPS. If you calculate the performance of processor 1 and processor 2 on some other program, then it will give some other MIPS value. So again, which is not reliable. And third drawback is MIPS can vary inversely to performance. Sometimes it may give the result in a different way. It may say that the processor which is better compared to another processor, it may say that, assume that actually the first processor is better than the second processor. But when you use MIPS, it may say that second processor is better than the first processor. So let us try to understand this with an example. Assume that in a typical processor, the instruction of type A, it needs 1 clock cycle. An instruction of type B, it needs 2 clock cycle. An instruction of type C, it needs 3 clock cycles. Okay. Say that you have 2 programs. So this program 1, this is program 1. Program 1 has 5 instructions of type A and 1 instruction of type B and 1 instruction of type C. And program 2 has 10 instructions of type A and 1 instructions of type B and 1 instruction of type C. And this processor, let us assume the processor is running at 100 megahertz clock speed, right? Now the overall CPI can be calculated like this: CPU clock cycles by instruction count. So what is the CPU clock cycle for the first program? For the first program, CPI 1, it is calculated like this. There are 5 instructions which needs 1 clock cycle. So it is 5 into 1. And then there is 1 instruction which needs 2 clock cycles. So 1 into plus 1 into 2. And then there is 1 instruction which needs 3 clock cycle. This one. So plus 1 into 3. Okay. Into 10 to the power 6, because we are calculating MIPS, which stands for millions of instructions per second, divided by how many instructions. So all these are in terms of instruction count in terms of millions. Okay, so we are multiplying by 10 to the power 6 divided by 5 plus 1 plus 1, which is 5 plus 1 plus 1 into 10 to the power 6. So this 10 to the power 6 and 10 to the power 6 will be cancelled. The result is 1.53 for CPI 1. Now, what is the formula for MIPS? MIPS is clock rate divided by CPI into 10 to the power 6. So this CPI we have calculated 1.43. Clock rate is what? Clock rate is 100 megahertz. Okay. Clock rate is 100 megahertz. So 100 megahertz divided by 1.43. which is nothing but 69.9. It is 69.9. Okay. Similarly, you can calculate for CPI 2 for the second program. The second program, it is 10 into 1 plus 1 into 2 plus 1 into 3 to 10 to the power 6 divided by 10 plus 1 plus 1, which is 1.25. Right? Again, it is 100 by 1.25. 100 by, so basically it is 100 by 1.25, so into 10 to the power 6, but this megahertz can be represented as 10 to the power 6, so that will be cancelled out. Okay, the 10 to the power 6 and 10 to the power 6 will be cancelled. 100 by 1.25 is nothing but 80. Okay, so now as per this calculation, it says that MIPS 2 has a higher value and MIPS 1 has a lower value. So which means that the program 1 performs better than program 2. Compiler 2 has a higher MIPS rating and it should be faster. But let us calculate the performance using some other technique. Let us take the CPU time. How much CPU time is required for both this program? So CPU time is calculated like this: instruction count into CPI by clock rate, right? So in the for the first case, how many instructions are there? 7 instructions. 5 plus 1 plus 1, 7. So it is 7 into 10 to the power 6 into CPI is, we have calculated here 1.43 for the first program. So 7 into 10 to the power 6 into 1.43 divided by clock rate is 100 megahertz. So 100 into 10 to the power 6. This 10 to the power 6, 10 to the power 6 will be cancelled. So 7 into 1.43 by 100 is 0.10 seconds. Okay. But CPU time for the second program, when you calculate, it is how many instructions? There are 10 plus 1 plus 1. So 12 instructions. 12 into 10 to the power 6 into 1.25 divided by 100 into 10 to the power 6. Again, this 10 to the power 6 and 10 to the power 6 will be cancelled. Now, if you calculate, you will get 0.15 seconds. So now you can say that CPU time 1, for the first program can be executed in 0.10 seconds, whereas second program needs 0.15 seconds, which means that first program is faster than the second program, despite the lower MIPS. Right? So MIPS is also not a effective method to measure the performance. Right? Okay. Let us stop here for today's session. Thank you.